Does that show up?
Yes.
Yeah, looks good.
Yeah, so the concept here is I want to run moon bounce. The skip season is only 6 or 8 weeks here. And what do you do the rest of the year? If you want to get real distance, you need moon bounce. But as I discovered, it's hard. It's real hard. So we have this little presentation here. Why is it so hard? Well, um, I'm clicking around here because it's made of
Ah,
rocks.
okay.
All right. Maybe I should call it an ed talk, huh?
That's awesome. Yes,
All right.
it's a very
Well,
talk.
so I did some research on seriously here, and the more I read about what happens to a signal as it goes from here to the moon and back, the more it broke my mind on this. And just as an academic exercise, I thought it was extremely interesting. All the things that can happen to the signal that makes this moon bounce so hard. I think you'll find it interesting too. Um, at the end of all this, you will run screaming from moon bounce. You'll never want to even touch it, but don't despair. It can be done. And in fact, it can be done from a rover station. Anyway, I'll talk about all these things you see here on the screen. And this whole presentation is more a matter of here's what happens, and not I'm not going to talk much about how we mitigate all these problems, but it's there. So, all right. Concept, transmitted signal illuminates part of the moon, part that you can see from the transmitter, and then somebody else gets a weak reflected signal. And you can already see some of the problems here to run moon bounce. For example, both stations have to be able to see the moon, physically see the moon. Okay, there can be clouds in the way, but your transmitter and receivers have to be able to see the moon there. And if you're really far apart, the shared part of the moon that you're illuminating, well, that gets smaller and smaller the further apart you are. So that's kind of a problem. We'll revisit other parts of the problems we have on this slide here in a minute. So transmitter goes to the moon, we get a reflection back. How far is that? Well, it's kind of a problem. 250 million miles each way. So about 2.5 seconds round trip. And as a matter of comparison, the moon's about 2,000 miles diameter. That's about a quarter of the size of the Earth. It's actually pretty big out there, but it's pretty far away. So the apparent width in the sky is about half of a degree. All right, let's dive into this for a second. What is, practically speaking, a half of a degree? I know you look out the window at night, you've seen the moon a bunch of times. So I want you to do this little exercise wherever you are. Stick your arm out straight and make a fist and poke your thumb up. And for almost everybody, the distance between the bottom of your hand and the top of the thumb, that's 15 degrees. And it scales nicely, by the way, as smaller people have smaller hands and it's closer in. It works out to be 15 degrees. 15 degrees is, in fact, how much the sun, or for that matter, the moon, will move in an hour. 15 degrees. You take 360 degrees around a planet, divide it by 24 hours. Simple mathematics says 15 degrees. This is kind of handy, by the way. Now that you know how much 15 degrees is, if you want to estimate time, you can hold your hand out and take, for example, in the evening, take a sighting on the sun and turn your hand so it's going the arc of the sun is going to go, and you could count out real easily how many hours till sunset because it's 1 hour per each 15 degrees. Um, and I hope everyone knows the apparent size getting larger at moonrise and moonset, the harvest moon and all that stuff. It's just an optical illusion. And convince yourself sometime that it's an optical illusion. All right, so let me get back on this half a degree. For my hand, I measured it's about 6 inches for my 15 degrees. Well, we want to know what 1 degree is, so you divide that 6 inches by 15 to get one degree out of that. And it turns out for me, my my one degree is about my pinky thumbnail is about 1 inch. So let's see. No, it's my pinky thumbnail is about half an inch. I just measured it. That's about 1 degree. So the moon in the sky is about for me, half of my pinky thumbnail. It's not very big. Try it yourself next time you see the moon and see how much of some thumbnail the moon subtends. Kind of interesting.
Yes. It's 2 hours.
Is that Mike? You might want to mute until you have a question.
Okay.
All right, thanks. All right, so this distance is quite a bit, and then you can see it's going to come into a loss of signal along the way. Directly attributable to the path loss is, well, let's see. Directly attributable to the path loss is this 1/r², 250 million miles out, 250 million miles back. You don't get much back, but what arrives at the moon, turns out the moon is a really poor reflector. It's lousy up there. Someone needs to go up and polish the moon and make it a lot more reflective, because we're only getting about 7% of the signal back. I found on the web somewhere, someone analyzed a very sharp antenna. They had 16 degrees beam width. It is very sharp. With that 16 degrees, a cone going out into space aimed at the moon, and the moon being only half a degree wide, only 1% of that energy hit the moon, and 99% of it escapes into free space. I hope aliens somewhere pick that up and do something with it. That'd be fun. Well, this was a very sharp antenna. And, I thought it was pretty hot stuff when I started roving with a 5-element beam out there, because really nobody was traveling with a beam that big as a rover. Well, it turns out my 5-element beam, it's an M² 6M5 XHP, has a 40-degree beam width. 40 degrees. So no wonder I was not having much success when I tried moon bounce with that particular antenna. Now, I think Ed has an LFA and a little better 5-element antenna. If so, he might have as much as a 25-degree beam width. If it's full length, shorter antennas, your shortened 6-meter beams, they directly lose beam width is what you give up on that. Anyway, 25 degrees is a lot more than 16 degrees for this one example I found. So that's pretty bad. All right, well, regardless of what antenna you use, the path loss is huge. 240 some decibels on 6 meters. And it's worse than that, guys. The moon gets a little closer and a little farther away, and that will add or subtract about 1 decibel. And just so you know, the phase of the moon, how much is illuminated by the sun, whether it's night or day, doesn't make any difference at all. 240 some decibels. That's kind of bad, by the way, but it gets worse. Let's talk about polarization. Polarization is 2 antennas that we're talking about horizontally polarized or vertically polarized antennas. They lose signal if one of them is tilted with respect to the other. It just depends on the cosine of the angle, right? So if they're in the same plane, the cosine is 1, you have no loss. 45 degrees, it's widely accepted, you lose 3 dB. If they're 60 degrees to each other, 6 dB, and eventually when they're 90 degrees to each other, you basically lose all signal. And this, by the way, is why we can use a metal mast with a horizontally polarized antenna. As long as they're at right angles to each other, there's no coupling. So that's good. But if you had a vertically polarized antenna then your mast being in the same plane is a problem. And you'll either need to have a non-conductive mast or suspend it from a sufficient distance off the back end of the antenna. But that doesn't matter. Polarization loss is a big thing in moon bounce. Because what this means, shoot, this was supposed to be something I could step through, for example. All right. Here's a guy on planet Earth. He's looking at the moon, and I've got a guy on the moon holding up a reflector. Really, it's the moon itself is our reflector. So that horizontal Yagi is shooting a horizontally polarized signal to the moon. It reflects off in the same polarization. So to get the most signal back, you need a horizontal antenna on Earth at the receiving side. Well, guess what? He's partway around the planet. So when he's standing up, horizontal to him is now vertical to the other guy. As you move around the planet, one horizontal is not the same as the other. All right, you got this? I mean, this is one of the more mind-bending things as you move around the planet. This spatial polarity is changing. Okay, nobody's asking a question yet, but this is spatial polarity loss. But this is just the start of the polarity loss. It's actually a lot worse than this. That spatial polarity, as these guys apparently move across the face of the Earth, as seen by the guy on the moon, that geometric polarization changes over time. So here's a graph I pulled off somewhere. On the left is the polarization in degrees, and on the right is minutes after moonrise. So anyway, as seen by the moon, the orientation of the antenna changes as the moon passes overhead or the Earth turns underneath. So this polarization changes over time. Great. But it's actually worse than that. Faraday rotation is the effect on polarized signals. When it goes through the ionosphere, there's charged particles and a magnetic field which rotates the plane of polarization. And when they get reflected back, they get rotated again. So it doesn't cancel out going out and coming back. They actually add up when the other guy transmits and tries to go out and come back. And as a result of Faraday rotation, it's not only possible, it is common for one station to hear the other perfectly well, and the opposite station doesn't hear a thing, because Faraday rotation has basically turned the polarization perpendicular to his antenna. Well, one-way propagation is common, and there's absolutely nothing you can do about it except for wait for the field to change, because it changes over periods of 5, 10, and 15 minutes. A signal that you could hear but he couldn't hear you will likely come back. And it's really hard to tell as an EME station who can hear you, whether or not you can hear them. So a proposed solution to this changing the rotation of a signal would be to use circular polarization, because that Faraday changes only affects linearly polarized signals. So this is great. All you have to do is come up with a circularly polarized signal, and it's reasonably easy to do. You have a combination of horizontal elements and vertical elements on the same boom, and they're spaced out such that it reinforces rotating the signal going out. That's all well and good, but because it's reflecting the signal off the moon, a hard surface, if you transmit right-hand circular polarization, it comes back as left-hand circular polarization. So Now you either need a polarity reversal circuit on your antenna that you flip every time you send and receive, or two antennas, each with different circular polarization. That's going to be fun, right? So mostly moon bounce people don't use circular polarized antenna, and they suffer through these polarization effects. But that's not all. It gets even worse than that. You know the saying, the moon always shows the same face to the earth? No, that's not true. It wobbles a lot, and these different features do different things to your signal, because you may see one crater one day and a different crater the next day. Just in case you've never seen it happen, let's see if I can play a movie. Are you getting a YouTube player in your view?
Yes. Yeah.
This is wild, guys.
Yeah, I've seen something like this before. I think it was a stop action. It was different photos, but it did have the same effect. And I wondered about that. I had not heard of this before. But yeah, it does wobble, doesn't it?
Sure does. And what this means for bouncing a signal off is you see slightly different parts of the moon on different days.
Ah,
Wow. So that's libration fading. Fortunately, it's not a big deal on 6 meters, but the texture of the moon becomes important at shorter wavelength signals. But that's not all. It keeps getting even worse, guys. So Doppler shift comes up because at moonrise, the Earth is spinning, and where you are on the planet is rapidly approaching the moon until you're directly underneath it, and Doppler shift is 0. Then you're moving away from the moon, and you get a Doppler shift in the other direction. Not good, but fortunately, it's not a big deal at 6 meters. As you get up into microwave frequencies, these guys have to deal with it. You just have to keep the receiver tuned in the right spot, or open up the bandwidth so you can capture all of that. So not a big deal at 6 meters, but it still keeps getting worse. There's a time spread. Imagine, if you will, look at the graph. There's an incoming wave front, which might as well be considered planar. It goes to the surface of the moon, which is really rough. Well, some parts are a little farther away than others, whether it's a crater or off to the edges of the moon. It's a spherical surface. It takes longer. It's considerably more distant to reach the edges of the moon and reflect back. But this means the reflected wavefront can be scrambled with these various reflections by a couple of milliseconds. So this will strictly limit the data rate that you can send and receive signals with. Not a big deal at 6 meters. We're not trying to get the maximum data rate of this whole thing, but there's that effect too. Well, that's a good start, but it keeps getting worse, guys. The moon up in the sky passes across different constellations at different times. Because it's not in the same plane as our solar system, it actually apparently moves up and down by, well, what it says, 28 degrees, 14 degrees up and down. So it covers a lot of different constellations up there. Well, these constellations, some of them are very noisy. So when the moon passes in front of something that's super noisy, I mean, obviously the sun is one, but nobody's going to try to do moon bounce if the sun is also in the captured area. But yeah, there's a bunch of noisy places in the sky that can completely wipe out the possibility of doing moon bounce just because there's that much noise. We can predict all of this. Thankfully, there's software that will tell you what days are good and what days are bad. And all right. Well, sorry about that. Regardless, galactic noise is predictable, and there's software that tell you what days are good and what days are bad. And generally, we look at degradation below 3 or 4 dB, and those are really quite promising for making moon bounce contacts. Turns out one of the better pieces of software, in fact, the one I use is written by Lance W7GJ. It's called the GJ Tracker, and it can predict far in advance what days are good and bad. Okay, well, that's just galactic noise. It gets even worse. There's city noise. And unfortunately, nowadays, people in the cities are moon bounce operators in the cities are practically unable to run moon bounce at moonrise and moonset, because at those times their antenna is pointed at the horizon, and there's a lot of city out there too. And they pick up with their exquisitely sensitive antennas and receivers, they pick up all the city noise. So to avoid that, you use an LFA antenna, loop fed array, or you elevate to point it more up in the sky and not at the city. And my solution, of course, go roving, go to a really quiet spot. If you ever talk to Peter, AG6EE, that's his whole shtick. He does moon bounce with big antennas, and he's designed antennas that he can take portable and set up and run. If you're looking at my profile video feed on the right, you'll see in the background, there's my 7-element 6-meter antenna. It's attached to the truck, and it's a loop fed array. It's an LFA. And I'm hoping to get this antenna out in the field sometime soon and actually try it out. All right, we've covered a lot of really bad things. So what are some of the approaches we can use? If you look at the path loss, the space physics of path loss, they get worse at higher frequencies. 240 some dB on 6 meters, 10 dB worse than 2 meters, 10 dB worse than that on 440. But if you assume the equal physical length antenna, like the one in the background of my picture, is 32 feet long. If you had a 32-foot long antenna on 2 meters, you would have a lot more elements, and it would be a lot more narrow beam width and a lot more gain. And that will overcome all the additional path loss you have here. So it's actually a lot easier to run moon bounce on 440 megahertz, or even 1296 is pretty practical. I know a guy that has a 6-foot folding umbrella dish that he will take on vacations with him. It's a 6-foot metal fabric dish, and he runs moon bounce on 1296. Unfortunately, I'm on 6 meters because that's where the people are that are chasing all these grids that I go to. So that's the one I keep working with. As a rover, or anyone else for that matter, there is one bit of good news: ground gain. Ground gain is what you get when you have a horizontally polarized antenna that's down low. That is, the radiated signal also impacts the ground, and the reflection from the ground will add to your signal strength at some elevations and subtract from other elevations. So there'll be a lobe down usually 12 to 15 degrees above the horizon where your lobe is improved by 5 or 6 dB. And then as you look higher and higher, there's a dead spot because your signal is greatly decreased. The ground reflection subtracts. And then a little higher up again, you get a terrific boost. I've heard as much as 10 or 12 dB, and it's around the 20 to 25 degree above the horizon. And it's, I've actually seen that myself. I was in CN93 in Glass Mountain and looking at the horizon, and the signal came in pretty well. No, it was a moonrise, so it came in pretty well on the horizon, faded out completely, and then came back. This stuff works. On the flip side, if you do elevate your antenna, although you don't get the ground gain, you do avoid the city noise that's around you. Not a big deal when I'm going roving. Whew. That's the one bit of good news we get for small EMA stations. So what does this mean? If one wanted to go out, I've looked at this closely. If you want to go out and run moon bounce, what do you really need to get started? And the general consensus is if you have a 5-element antenna, you can certainly work the really big guns. They have fantastic antenna arrays, and they will make up for much of the capability that you lack. If you want to be able to work another station of the same size you are, 5-element is just barely enough to get there. You're going to want more. You absolutely need a low noise preamp and a kilowatt and a quiet location, and operate at a time when the moon is in a part of the sky that has low degradation. But there's a feature in WSJT where you can actually send a signal and it will listen for the echo off of the moon. You're not going to do that on this size of a station. Well, we've gone through a lot of problems. I'm about to wrap this up here. The conclusion, I'm sure you all recognize, is this is difficult. This is hard stuff. There's a couple of nice parts about moon bounce is that it works year round and it's more usable, more doable during the 3 or 4 days, twice a month that you get low degradation. So one can plan your rover trip to a quiet location around those days in the month. And if you don't have elevation, that is, if you can't tilt your antenna up toward the sky, then you get at least 2, maybe 3 hours where the ground gain will really help you out. And after 3 hours, the moon has moved up out of the aperture, the cone of your antenna that goes out there. And if you talk to Lance about his expeditions to rare islands, he has lots of extra time to go scuba diving and whatever. I didn't mention here, but those doable twice a day, yeah, you get moonrise and moonset, but that's not necessarily at sunrise and sunset. One of those may be at midnight or who knows what time of day, something that's really not very convenient. And finally, if you have a specific station that you want to reach, you'll have some common time, at least once a day, sometimes twice a day, depending on the declination of the moon, where you can both see the moon at the same time. So that's kind of nice. I've been looking at going to Texas. Big Bend National Park is the #1 most rare grid, DL88. And it's the most rare because nobody can live there. Nobody wants to live there. It's a national park. There's a lot of stringent rules just to get in there and set up and operate. And it's only a couple miles wide in the United States. Most of it's in Mexico, but the parts in Mexico is completely controlled by the cartels, and you don't want to go there. And the Mexicans, all the ones I've talked to, don't want to go there too. Anyway, moon bounce would be a solution, I think a good solution for me. If I pick the right days to go to Big Bend National Park, I can do it any time of year. I don't have to wait for skip season. So I'm looking at November. There's some good low degradation days. That might be the time I go. Whew. So that's the mind-bending space physics involved in moon bounce. And my closing slide, Ed and I have both been out to visit Lance, W7GJ, and here's a picture of his antenna farm. And the little guy over here on the right, that's his 6-meter moon bounce antenna. It says 4x6 element. It's actually 4x9 element. I wrote that wrong. 9-element 6-meter beam and 4 of them. I'm sorry, that blows my mind. I'm not gonna carry that on an expedition. All right. Thank you all for this highly depressing look at moon bounce. I hope you enjoyed it.
I think it's
Thank you. That
awesome.
was
Thank you,
awesome.
Barry. Yeah. Especially great because you're the one going out. We can bask in your glory if we make these connections. Yeah. Lance sets the bar for a lot of things, but it kind of impacts you and I also. I get I don't know how many comments, at least a few every day. Hey, I made it to Montana. I'm being heard in Montana. Well, they're talking about Lance with his 3,000 elements on 6 meters. Like, well, that's great,
Yeah.
but
And that's just his array. The one on the tower in the background, that's a gigantic 6 meter antenna. It has a couple of giant support ropes above and below it. Oh yeah, that's the 9 element antenna. And these really are 6 element antennas on the array down there, and a 9 element single antenna. Good grief.
Where is this antenna farm located?
It's in Montana. It's not far off of I-90. It's Ed, what's the name of that town he's by?
the French town,
Frenchtown, that's right.
yeah, just west of Missoula.
Barry had one comment. Your distance to the moon is off.
Oh no.
Oh, yeah.
250,000 miles.
Yeah, yeah. That rings a bell now that you mention it. Something was wrong there.
Yeah.
That was a test. You passed.
Maybe. It just seems like it's farther away and much smaller.
It might as well be a million
God.
Yeah.
Have you had any successful contacts?
I have been heard off of the moon, and I have heard people off the moon. I have not made a contact yet. And I looked closely at my equipment. I got a low noise amplifier and single band 6 meters, and that helped. But if my 5 element by M squared is just not up to the task. It's a fabulous terrestrial antenna. I think it's magic for contacts across the earth, but it's the one with a 40-degree beam width. That's just not going to cut it on the moon.
Barry, this is Chuck.
Yeah.
Yeah, how about setting up on the beach, reflecting off the ocean? Would that make it a little better for you?
Yeah, that sounds like a good idea.
That's a good idea. In fact, that's what Lance does. He finds places on the beach. Of course, almost everything is beach for the little islands that he goes to. For me, the optimal location is to be on a high hilltop, a horizontal antenna, and I park within a wavelength of a drop off. And if you get a slope of 10 or 20 degrees going down in the direction toward the moon, then that's where I will get the greatest ground gain, because it has the lowest first lobe and a really good second lobe above the horizon.
So do you use a checklist or something to get all these things to line up so that it'll work? I mean, that's a lot to think about.
That's actually a good question.
Yeah, every single one of these things there's nothing you can do about it. A Faraday rotation, okay, we have no control. We just wait it out and work someone else. Spatial polarity loss, nothing you can do about that. You just wait it out. The libration fading, nothing we can do. But it's not a big deal on 6 meters. Doppler shift and time spread is not a big deal on 6 meters. So it really boils down to, I run GJ tracker and I find the days of low degradation between less than 3 or 4 dB, and I operate on those days, and I have a chat window with whoever I'm trying to work on the side. And at least then I know that they're on the air and they know that I'm on the air, and we'll keep pointing at. Hey, one interesting thing, when you're out there, yeah, the moon moves at 15 degrees an hour, but that only means about every 10 minutes I step outside and nudge the antenna just a little bit, and I'm tracking the moon. That's all it takes. You don't need an expensive tracker and software to do that. The hard part, frankly, is setting up Q65 perfectly.
Mm.
Q65 has a lot of settings, and it is easy to miss one of those. That's where I do have a checklist.
Yeah, I do that just for my simple stuff. I have a little field book that's wedges below the radio on the rack to remind myself of all the settings, all
Yeah.
those modes. You get tired and it's like, oh gosh, what did I set that at?
Yeah, and that's gotten better since I've made a different profile, a different rig profile in WSJT. So when I switch to Meteor Scatter or Q65 or FT8, I don't go in and change settings. I close this profile and I open the next profile.
Yeah,
Then it's pretty well set.
So Barry, I might have missed it. The communications then is a phone, FT8. What are you?
It's Q65.
Okay.
And Q65 will average the waveforms that it receives over a couple of cycles. And it's Q65 mode A for 60 seconds is the convention right now.
you power down a little bit, Barry, when you're doing 60 seconds, or there's a discussion just recently about that. Do you let your amp run for 60 seconds?
I keep it powered up until it complains.
Yeah.
I'll push it for all I've got. So for the amp that I have, I need to raise it off the desk a couple more inches because it has a fan on the bottom and a fan at the top, and it draws air up through that. Okay. So I want to make sure the bottom has all the air I can possibly get.
Yeah.
It draws down my battery, I tell you that. Oh, local noise. My kilowatt amp runs from a 48-volt battery, and I have 5 kilowatt hours in the batteries, and I'm pretty good for 3 or 4 hours, and then I've got to recharge that battery.
That's remarkable.
But there's no inverter, so there's no inverter noise.
Yeah, inverters.
And that helps. Yeah. One of the biggest noise sources in my van right now, frankly, it really pisses me off, is when I stick my watch, an Apple Watch, on the charger, it generates a hash. What's up with that?
Oh.
I'll tell you though, Arduino has no noise on 6 meters.
There we go.
So some of them are really bad though. I bought an Arduino, one of the Wi-Fi ones. It was terrible. It had a really bad what was it? Voltage regulator. I think like this was known on the internet. It had a really bad voltage regulator that was blasting out all sorts of garbage.
Wow.
On I think it was on 2 meters, not 6, but it was really, really, really bad.
Before I got my 48-volt battery, I had an HP 50-volt rack server power supply. And these are very popular for driving these big 50-volt kilowatt amplifiers, right? Very popular. I have ferrites all over it, and it's still noisy. That's part of the reason I gave up on that particular power supply. So if anybody what is it? It's about a 2 kilowatt capable 50-volt power supply. I'll sell it to you. Just don't try it on 6 meters.
Yeah, I was gonna say, sort of burst the bubble even before before we put it
Yeah.
up for sale here. But
I don't know. It's not that bad, but yeah, it is that bad.
well, you
Anyway,
go, yeah, you go out. It's a long way and it's a big expense, and you don't want to hinder yourself.
Yeah.
Right out the gate.
once my kitchen remodel settles down here, I'm gonna go out for a shakedown cruise somewhere and try to work some people off the moon. That would be really fun. There's some really big guns out there. Some guys in Sweden. My God, I don't know what they have, but they work everybody. I want to work. My favorite station to work is I've kind of adopted TAC JA7QVI. Really a humble, nice, and highly capable operator in Japan, and I've worked him from many of these rare grids that I've gotten to. He's one of the few people outside our country that's chasing FFMA. So it'd be really fun to work him up the moon. So there we are.
There we are. Thanks, Barry.
Thank you.
That's
Thank
actually
you.
really good. That's really good.
Yeah, thank you, Barry.
Yes, thank you, Barry.
Yeah, quite welcome. Should I email this presentation to the group? I don't know.
Sure.
I think it'd be great if you want to, or we can put it online somewhere. And I am recording. I did remember to hit record this evening, so we'll have that available someday on our little YouTube channel as well.
Okay.
That'd be awesome.
Yeah, well, good.